All right, this may be our final in the lecture series because I think it pretty well covers the AP2. I'll double check, see how far they go into induction, but this is probably about it. So today is all about how do you induce a EMF. And so we have two laws today, one about Faraday and one about Lenz. You've heard about Faraday probably more than you have about Lenz, but both made pretty important contributions, and we're going to do a whole lot of right-hand rules today. So let's get it started. So Faraday's law is about a changing field to create an electric field. So we already talked about a charge, a moving charge makes a magnetic field. Now we're going to kind of do the opposite. We're going to actually move a magnetic field to move a charge. Kind of going to work in reverse. Okay, so we looked at magnetic fields, forces on charges and currents, torques on loops, that's how a motor works, and a magnetic field due to long straight wire and a solenoid, which is a coil of wire. So we looked at torques on current loops. Today we're actually going to look at the opposite of that, which is a generator. So this is how a motor works. So today we learned how a generator works. It's just in reverse. So I guess yesterday we learned about how a speaker would work, because a speaker is a motor. Today we're going to learn how a microphone works, because it works just backwards from it. The microphone is a generator, in fact. Alrighty, so a little summary of our right-hand rules. There are lots of them, and I do them a little bit differently. Like the way to do the first one, that's pretty popular with the, remember the thumb points the direction of the velocity of a charge, a positively charged particle. Do remember to use your left hand if you're doing a negative charge, okay? Because otherwise you got to remember it's the back of the hand, and I think it's a lot easier to say, hey, you're right-handed. 95% of us are right-handed, so it's just easier to work with. And if you do have a negative charge, you just switch to the left hand, and everything works the same. It's just the left hand, okay? So the hands point in the direction of the field, and the force is where the palm is. So the second right-hand rule is the straight one. I like to do the curl. Okay, it's for a straight wire. It's confusing because it looks like it goes with the solenoid. It doesn't. You look at the straight wire and you look to the right. Those are the same two right here. This straight wire and these two go together. This one goes together with that one over there. Okay, it's pretty confusing. So what happens is your thumb still points in the direction of the charge, positive charge flowing, but I like to wrap my hand around it. So I could do the fingers. There's the field. I could wrap my hand like this, and there's the field. I like to wrap my whole hand around there. Okay, and that shows me the magnetic field circulating around the wire, which is this picture right over here. Okay, just grab it, and my hand, so the magnetic field is pointing that way there. It's pointing this way on this side as it circles around. The second, I guess they're doing, maybe that's the alternate. I understand now. This is the better one, but they're doing the same thing for right-hand rule number 2. This down here is a right-hand rule for number 3. This one right over here, because this one is helpful to find north poles when you're dealing with coils of wire. Okay, and specifically what that is for this one is your hand wraps in the direction of the current. Okay. Your hand wraps in the direction of the current, and then your finger points to the North Pole. Okay? So as I'm looking at this hand, in fact, that's a little... okay, so yeah, the current's going in that direction, so the hands wrap in the direction that the current goes, and then the thumb points to the North Pole. That's my third one, an R8, an RHR3. Okay, because that's two different things going on. That's for a single wire. This is for a coil. We're going to use the crud out of this today, and we'll do a little bit of that today as well. Okay, well, of course, we're always doing that one. All right, next slide. So here we go. We got a metal bar slide with a velocity v on a track in uniform B. Hey, pop quiz. What direction is the field of these pink dots? What direction is the magnetic field? Towards your face. Because that's like a missile coming right at you. If it was away from it, if the field was into the screen, it would be X's. If the field was to the right, they would show arrows going to the right. If it was to the left, they would show in those directions. So we're doing a 3D thing here. So because we have vectors that are acting in 3D, something has to be in or out of the page, and the author chose this to be the magnetic field coming out. Alrighty, so you have a metal bar sliding at some speed along the uniform field that direction. Well, so on this bar, it's conducting bar, and those are conducting wires, and there's a light bulb. No battery source, you'll notice, none at all. So if you have, there are charges in everything, there are charges in this conducting bar. So if all those charges are moving to the right in a magnetic field, which way are they going to be pushed? Well, start with your rule number one, right hand rule number one. So the hand points, the thumb points in the direction of the charges. So there are charges that are stationary on that rod when it's stationary, but as soon as you push the rod to the right, those same charges are now moving to the right. Positive and negative ones alike. We'll talk about the negatives in a second. So positive charges, well, if you wonder which way they're going to get pushed, that's where you need your hands to go in the direction of the field. The field is pointed at your face right there. It's coming out. So if the charges are going to the right, even though they were stationary, there's actually a magnetic force downward on those charges. And now we have some work being done because we're pushing charges from the top of the bar to the bottom because we're setting up what's called an electromotive force, a potential difference across the bar. So that just the very fact of that going makes a potential difference. Turns out an airplane, a metal airplane flying through the magnetic field of the earth, the same thing can happen. You can get an EMF, a difference between the two wings as you're cutting across there. So if the field is pointing out of the earth, like if you're near the South Pole there, the field is pointing out of the earth. Whoops, my bad, because the North Pole is the South Pole, right? So the field lines are actually pointing, so they're pointing out of the north to the south. So if you're near the Antarctic and you're flying an airplane in Antarctica, you would actually be doing the same thing. You would push positive charges to the right side of your airplane, and negative charges would be pushed to the left, because that's the left-hand rule, right? So negative charges, well, they'll still go in this direction. The field is still out of the page. That means negatives are being pushed up. Positive charges are being pushed down. That's the right-hand rule. You have a potential difference across your airplane wings. So you could set up a little circuit if you wanted to, maybe through the tail or something. Okay, so we're going to talk about today, what would you have to know to find that potential difference? Alrighty, so by right-hand rule number one, you're actually shoving charges down this way of a potential difference, and you can actually set up a circuit and induce an EMF that goes in the clockwise direction if you indeed move to the right. Oh, there it is, guys. Did you feel it? Were you blinded by the light? So there are charges in here that were stationary, and some still are, but because it moved that way, there was a magnetic force that pushed them downward as a result of that. That's their first right-hand rule. They're pushed downward. So that positive charge experiences a force downward. That's the right-hand rule. And so the current is driven clockwise through this thing. And they said, let there be light. Okay? So electrons move, but they move in the opposite direction. That's your left-hand rule. We just talked about that a second ago. Okay, so the bar acts kind of like was as a source of potential. Okay, it generates an EMF. Couple things where we're going with this thing today is, notice we have an increase in field lines in here. We're increasing the flux. That's where we're going with Lenz's law today, is going to help us find out what happens when we have an increase in flux. It'll also help us determine more quickly what direction it must be flowing. Okay? Well, more on that in a moment. Alrighty, so here's all about Faraday. What he found out is the reason we have an EMF is because we have a change in flux. So flux are the number of field lines. Remember we talked about flux with Gauss's law, and we talked about the permittivity of free space. Now we're talking about the permeability of free space and magnetic flux in Tesla. Well, Tesla is a magnetic field. So it's Webers per square area is a Tesla. But so flux is going to be measured in Webers. That's not actually going to come up on this PowerPoint, but we're just going to call this flux. And we have an increase in flux. So if we have an increase in flux per time, that's going to create an electromotive force. Now you notice there's a negative on there because it's actually called a back. It's called a back potential. So in other words, it's going to be going, and we're going to call that clockwise a negative direction, at least for now. It's going to be a backwards. Now, if we moved it the other way, we'd have a decrease in flux. We'd find out the current actually goes the other direction. Okay? So, for example, if now you're forcing the thing to go backwards, and that magnetic field is outward, and you're forcing it to go backwards, now the force is upward, you're actually going to cause it to go the opposite direction if you go this way with a decrease in flux. Okay? But that's his law. All you have to find is the difference in flux per time. So that means the faster this happens, the faster you move that bar, the less time it takes. With the same change in flux, the greater the electromotive force. So speed has a lot to do with it. So flying that airplane faster is going to make a greater potential difference across the wings as you cut across the magnetic field lines of the Earth. All right, so the principle that unifies electricity and magnetism, key things into E&M. So you generate electricity, how your microphones work. It's the opposite of speakers, because speakers actually use a changing EMF to do work to push push the air around to make a vibration. So it's actually more how microphone works, but a guitar pickup acts like a microphone because you have a metal changing the amount of flux near that coil of wire. So we have a lot of things that work off this process. Okay? Alrighty, so magnetic flux counts the number of field lines through the loops. That's what the flux is, the number of lines. The more lines you have, the more flux you have. Okay? So uniform magnetic field B passes through a plane of that surface A. Alrighty, so magnetic field is actually your flux per your area. That's how you define what a magnetic field is. It's your lines of flux per area. But we don't really measure the flux normally, but you can calculate it more easily if you know if you measure the strength of the magnetic field in Tesla times your area. So Tesla meter squared is the Weber. Okay? So that's how you would find the actual flux. But what we care about is not the actual amount of flux, it's your change in flux, because that's going to tell you what kind of EMF you have. So the faster you change that flux, the greater the induced EMF. So as you notice, as you rotate this from from down here, we have a decrease in flux, because what we're looking at is the normal to the area vector. Because once again, this is a vector and this is a vector, but we're looking at the area vector to this. So when these are in the same direction, that's maximum flux. Okay? But as you rotate that thing, the area that has the flux going through it is actually going to get smaller as the area vector. So now we're going to have to do some trig here. And so what happens is, as long as the area vector is in the same direction as the flux, that's maximum, because there's zero angle. Cosine of 0 is 1. But as you rotate to 90 degrees, now there's a 90-degree difference between the field and the area vector. Well, cosine of 90 is 0. There's no flux through the loop whatsoever. So the theta angle is between the area vector and, of course, the magnetic field. Alrighty, note the flux can be negative. The field lines go through the loop in the opposite directions. Yes. Okay? So as it flips over, you could have a negative flux through the thing. Alrighty, so compare the flux through the two loops, A and the B. Which one has more flux going through it? This doesn't really have any flux going through this. Okay, so this is your loop. It's hard to kind of see it. So the current could go in one way and come out the other way. So there's a loop here. Okay, so you're looking at maybe the current goes that way and comes back. Just probably put an X in there, but whatever. This is what your loop is. Here we have maximum flux coming through. There's minimum. So the flux through A and B, of course you have more flux through the A than the B. As it turns to 90, you have no flux. As it rotates further, you get a little bit more flux through the thing, but the area vector is going to be pointing in another direction as you flip around, and eventually it's going to be the current's going to go in the other direction. That's how a generator works. Okay? So today we're talking about generators. By changing the flux going through this loop, we get a greater EMF on the loop, and that's how we generate electricity. Okay, so more lines means more flux. Alrighty, so induced EMF, rate of change in magnetic flux. The faster we change that, the higher the EMF. Okay, so normally we don't measure that, but what we can measure is your magnetic field in your area. So to find flux, you're going to have to do this stuff first. Okay, you're going to have to find the magnetic field in the area, then find the time it takes for that to change from maximum to minimum to 0, and so on. So there are actually three ways to change the flux. One is you change the magnetic field, or you can change the area, or you can change the angle. So